This video covers problem 3 on binary number representation, focusing on converting decimal numbers to binary and understanding floating point binary representation. Here is the full question for problem 3. We'll determine the binary representations for 625, 6.25, and 0.0625. Then we'll examine the infinitely repeating binary representation of 1/5 and determine the stored value and error for 0.2 given an 8-bit storage limit. Base 10 or decimal uses powers of 10 for position weights. Binary or base 2 uses only digits 0 and 1 with position weights based on powers of 2. For fractions, positions to the right of the point represent negative powers of the base. To convert 625 to binary, we express it as a sum of powers of 2. 625 equals 512 plus 64 plus 32 plus 16 plus 1, which corresponds to 2 to the 9th power plus 2 to the 6th, 5th, 4th, and 0 power. The binary representation is 1,001,110,001 with a base of 2. For 6.25, we write it as 4 plus 2 plus 1/4, or 2 squared plus 2 plus 2 squared. Combining the integer and fractional parts gives us 110.01 in binary. For 0.0625, recognizing it as 1/16, or 2 to the power of -4, results in 0.0001 in binary. A fraction can be expressed exactly in binary only if its denominator is a power of 2. Since 5 is not a power of 2, the binary expansion of 1/5 or 0.2 repeats infinitely as 0.00110011. With 8-bit storage, 0.2 is represented as 51/256. The resulting error is 0.2 minus 51/256, which simplifies to 1/1280th. The absolute error is approximately 0.00078125, which is less than 0.1%. Absolute error is the difference between the true value and the stored value, having the same units. Relative error is dimensionless, often a percentage, and better indicates accuracy regardless of scale. For example, a small relative error indicates a good approximation. The key takeaway is that non-terminating binary fractions, arising when the denominator is not a power of 2, are a fundamental source of floating point error in computers, as they only store finite bits.